When we think about the history of life, we often picture this slow, steady climb. But, the universe is actually a pretty violent place.
It really is. And evolution doesn't just happen through subtle competition. Sometimes, maybe often, it springs directly from absolute catastrophe.
Yeah, like hitting a giant reset button.
Exactly. And that's our mission today. A deep dive into maybe the most famous reset button event, the late Cretaceous-Tertiary extinction, usually called the KT event.
Right, 65 million years ago.
Uh-huh. We're looking at how the massive destruction that, well, wiped out the non-avian dinosaurs really paved the way for this incredible explosion of the survivors.
It's like the ultimate story of evolutionary opportunism, isn't it?
Absolutely. But before we get to the survivors, we need to appreciate the scale of what happened. Our sources break down extinction into different levels.
Okay.
First, you've got the loss of just a single species. Sad for that lineage, but localized.
Right. Happens all the time, unfortunately.
Yeah. Then you scale up to mass extinction. The usual definition is when you lose half or more of all species in a region, or even globally. The KT event definitely fits that bill. It was devastating.
But not total annihilation.
No, not total. Pockets of life survived, which is key.
And then there's the really scary level. Global extinction, like snowball Earth, 635 million years ago?
Yeah, that was something else. The whole planet basically iced over for, 10 million years. Nearly wiped out all complex life. The KT wasn't that extreme, thankfully.
But still powerful enough to completely change the course of life, especially for mammals.
And what's really fascinating and unique about the KT boundary is it's the only mass extinction we can conclusively link to an asteroid impact.
The only one.
The only one with really solid smoking gun evidence. But the outcome, the rise of mammals, it just hammers home this point. Being dominant yesterday means absolutely nothing for tomorrow. Evolution's path is, well, fundamentally unpredictable.
Okay, so let's get into that evidence for the KT impact. People argued about volcanoes versus asteroids for ages. What was the clincher? What pointed definitively to space?
The big one was iridium. It's an element that's super rare in the Earth's crust, like 0.001 parts per million, maybe.
Tiny amounts.
Right. But it's much more common in meteorites. And right at the KT boundary layer, this thin geological stratum found worldwide, the iridium level suddenly jumps. We're talking up to 0.5 parts per million.
Whoa, that's a huge spike, like finding gold dust everywhere.
Pretty much. It's a clear chemical signature of extraterrestrial material raining down globally after an impact.
And it wasn't just chemistry, right? There was physical evidence, too.
Oh, absolutely. In that same layer, you find these high-impact particles, things like glass-like spherules, basically tiny blobs of rock that melted in the impact, got thrown up, and flash froze.
Molten rock rain.
Yeah. And also shocked quartz grains that have these microscopic fracture patterns that can only form under the immense sudden pressure of a massive impact.
And all this pointed to one place.
It all pointed towards the Chicxulub crater, just off the Yucatan Peninsula in Mexico.
Which is just enormous. What's the estimate? 185, maybe 200 kilometers across?
Somewhere in that range, yeah. It's one of the biggest impact structures in the inner solar system since the really early days, the heavy bombardment period.
But you mentioned it's not just the asteroid. It gets more complicated.
Right. This is where the simple story breaks down a bit. It wasn't just a single knockout blow. You absolutely cannot ignore the massive volcanic activity happening around the same time.
The Deccan Traps in India.
Exactly. We're talking about an unbelievable outpouring of lava, 4.1 million cubic kilometers, covering about a third of India. That much volcanism would have drastically altered the atmosphere, the climate, everything.
So the planet was already stressed. There was also that warming period just before the impact, right? Like 7 or 8 degrees Celsius hotter.
So you've got massive long-term volcanism pumping greenhouse gases and pollutants into the air, and the climate is already significantly warmer. The ecosystem was likely already fragile.
Which makes you wonder, did the asteroid just push things over the edge?
That seems to be the picture emerging. Paleontological evidence suggests that some large dinosaur groups were actually already declining before the impact. So the asteroid wasn't maybe the sole cause, but more like the final catastrophic blow to an already stressed system. It accelerated everything.
That makes so much more sense than some older ideas, like that orthogenesis theory.
Oh, right. Orthogenesis. The idea that species just had this internal clock, a predetermined lifespan, And they died out because, well, their time was up, or they developed bad traits like the Irish elk's huge antlers.
Seem maladaptive.
Yeah, we now know that's not really how it works. Extinction is driven by external factors, environment, competition, catastrophes, not some internal sell-by date.
And the KT impact story with the iridium is so different from the other really big one, the Permian-Triassic extinction.
Totally different. The Great Dying, 251 million years ago, up to 96% of marine species gone. Just catastrophic.
With no iridium spike.
Almost none, which points to different causes entirely. Maybe massive methane release from the oceans, maybe runaway climate change, severe oxygen depletion. Still debated, but definitely not an asteroid like the KT.
Okay, so the dinosaurs are out, the world has changed. Who inherits this new world?
The survivors. And in this case, crucially, the small stem mammals. They squeaked through.
What was their secret? What traits let them survive when the giant dinosaurs couldn't?
Two main things, it seems. Small size and efficient thermoregulation controlling their body temperature.
So being small and warm-blooded.
Pretty much. Being small meant they needed less food, which was suddenly scarce. They could hide or burrow, escaping the immediate blast effects, the heat pulse, the ensuing impact winter.
Right, sheltering from the dust cloud and the cold.
Exactly. Large dinosaurs couldn't hide, and their food sources collapsed. It's this great irony. The traits that made mammals relatively insignificant before the impact suddenly became their winning lottery ticket after it.
Talk about being in the right place at the right time with the right, previously unimportant features.
It's pure opportunism, and boy did they take the opportunity. Once the dust literally settled, mammals underwent this explosive radiation.
Filling all those empty ecological roles.
All of them. At least 25 major lineages appeared relatively quickly, specializing for life on land, in water, even in the air. Think about bats. They're the second largest group of mammals today. That's part of this post-KT success story.
And this massive diversification wasn't just happening in a static world, right? The continents themselves were moving.
Ah, yes. Continental drift. A huge driver. Pangaea started breaking up way back, around 225 million years ago.
Right.
And as these continents drifted apart over millions of years, they created isolated landmasses. Evolutionary islands, basically.
Which allows for unique evolutionary paths.
Precisely. Each isolated continent became its own evolutionary laboratory, creating new niches, driving diversification.
There's a great example of this in the source material about South America, isn't there?
Absolutely. For tens of millions of years, South America was an island. And on this island, marsupials and some very early placental mammals, the xenorhynths like sloths and anteaters, and some unique hoofed mammals, they radiated like crazy, filled up all the available jobs, ecologically speaking.
Until the land bridge formed.
Until the Isthmus of Panama connected North and South America about 5 million years ago, during the Pliocene. Then you had this massive influx of highly competitive placental mammals moving south from North America.
And the native South American animals.
Many of them couldn't compete. You see a wave of extinctions, especially among the native marsupials. It's called the Great American Biotic Interchange, and it's a classic example of competition leading to co-extinction. Radiation and extinction totally intertwined.
And speaking of extinction drivers, fast forward a bit. We get to the impact of humans. The late Pleistocene extinctions, around 11,000 years ago.
Yeah, this one's a bit more sobering, especially North America. We lost something like 57 out of 79 species of megafauna mammals over 40 kilograms.
Mammoths, mastodons, giant sloths, saber-tooths.
All gone relatively quickly. And the timing lines up disturbingly well with the arrival and spread of sophisticated Stone Age human hunters moving into areas previously covered by ice sheets.
So probably the first major man-made extinction event, combined with climate change at the end of the Ice Age, maybe?
That's the leading hypothesis. A combination of hunting pressure and rapid climate shifts proved too much for many of these giant animals. A stark reminder of our potential impact.
Okay, let's shift focus upwards to the air.
Yeah.
Flight is obviously a massive advantage, and it evolved multiple times independently.
Right. Sustained powered flight evolved separately in 3 distinct vertebrate lineages. Pterosaurs, birds, and bats.
3 completely different solutions to getting airborne.
Exactly. Pterosaurs came first, late Triassic. They flew with a membrane stretched along an incredibly elongated 4th finger. Amazing creatures, but they died out at the KT boundary along with the dinosaurs.
Okay, so they didn't make it through.
Nope. But birds, which evolved later in the Jurassic, did. Their flight system uses feathers, supported by a wing structure derived from 3 fused fingers.
And the classic example, the one everyone knows, is Archaeopteryx.
The icon, Archaeopteryx, is amazing because it's so clearly transitional. It has feathered wings, definitely capable of some flight.
But it also has teeth, claws on its fingers, a long bony tail.
Yeah.
Very reptilian, very dinosaurian.
Exactly. It screams dinosaur trying to be a bird. And modern science, especially phylogenetics, has completely confirmed this. Birds are dinosaurs. They're a living branch of the theropod dinosaur family tree.
So when you see a pigeon, you're literally looking at a dinosaur.
You are. And discoveries keep reinforcing this. Fossils like Xiaotinsha have helped place Archaeopteryx itself firmly within that dinosaur group. The link is undeniable.
What about feathers? Did they evolve for flight?
Probably not initially. The current thinking is that feathers appeared earlier in dinosaurs, maybe for insulation, keeping warm, or possibly for display, like showing off. We have fossils like Microraptor, a small dinosaur with feathers on all 4 limbs.
4 wings. Wow.
Oh, so flight was likely a secondary adaptation of feathers, and after the KT event, the surviving bird lineages just took off, radiating incredibly fast. Most modern bird orders trace their origins back to that period, around 60 to 90 million years ago.
And some were so successful on land, they even gave up flight again.
That happened too. Secondary flightlessness, think penguins adapting to the sea, or extinct giants like Diatrema in North America, often happened on islands or continents where there weren't many ground predators initially.
Okay, one more massive group to cover. The insects. Their numbers are just staggering. 900,000 known species. Maybe up to 8 million actually out there.
Yeah.
That's an explosion.
It's almost unbelievable diversity and abundance. Their success comes down to a couple of key evolutionary innovations.
What are they?
First is their modular body plan. Think of an insect's body like it's built from interchangeable modules: antenna, mouthparts, legs, wings.
Like biological Lego?
Kind of, yeah. It allows for what we call mosaic evolution. They can tweak one part, say the mouth parts, to feed on a new plant without having to redesign the whole insect. This allows for really rapid, fine-tuned adaptation and specialization.
Makes sense. Faster evolution. What's the second advantage?
Their hardened exoskeleton. It provides fantastic protection against predators and, crucially, prevents them from drying out. That was key for conquering land environments.
But it limits their size, right?
It does. The physics of supporting that exoskeleton and their system of breathing through tubes, Trichia, puts a practical limit on how big they can get on land. You don't see insects the size of those giant ancient sea scorpions, for example.
And then there's their social structure. Some of them enter.
Yes, social organization. This is huge for groups like termites, ants, bees, wasps. We talk about the superorganisms.
Where the colony acts like a single entity?
Exactly. You have this extreme division of labor queens that reproduce, sterile workers that forage and build, soldiers that defend, different body forms, different jobs, all coordinated.
How do they coordinate all that?
Often chemically. Hormones and pheromones play a huge role. Like, the queen might produce a pheromone that suppresses the worker's ability to reproduce, ensuring everyone works for the good of the colony. It makes the colony itself, not the individual insect, the unit of selection and survival. An incredible strategy.
So pulling this all together, this journey through catastrophe and recovery, what's the big picture?
I think the main lesson from this deep dive is just how unpredictable evolution really is. Success today guarantees nothing tomorrow, and extinction, as harsh as it sounds, is fundamentally intertwined with speciation. It clears the slate.
The KT event didn't just kill off the dinosaurs. It actively created the space for mammals and birds to flourish.
Precisely. It restructured life on Earth. It reinforces these core ideas. Extinction creates opportunity. Major evolutionary radiations are often tied to big geological events like continental drift. And specific adaptations, whether it's insect modularity or just being small and hiding like early mammals, can become winning strategies under the right, often catastrophic circumstances.
And we saw that the traits that helped mammals survive the KT, like being small and hidden, were the opposite of what made dinosaurs dominant before.
Right. The best traits are entirely context-dependent.
Which leads to a really interesting final thought. What traits exist today, maybe overlooked, maybe seeming neutral or even slightly disadvantageous right now, what might become the critical survival toolkit for whatever life inherits the Earth after the next big global change? Because change is inevitable, isn't it?
It certainly is. That's definitely something to ponder. Well, thank you for joining us on this exploration of evolution forged in the fires of catastrophe.
Yes, thank you for listening.